Assalamualaikum and hi everyone. Today, my teams and I will talk about crystalline solid for subject in organic chemistry, CHM361. The objective of this presentation are to define what crystalline solids are, to differentiate between crystalline and amorphous solids, to explain the different types of crystalline solids, and to relate crystalline solids to their application in everyday life. Introduction. Crystalline solids are solids in which atoms, ions, or molecules are arranged in a highly ordered and repeating pattern. This regular arrangement extends throughout the entire solid, forming what we call a crystal lattice. Because of this orderly structure, crystalline solids usually have a definite shape, sharp melting point, and consistent physical properties. Example of crystalline solid that we encounter in daily life include sodium chloride, metals such as iron and copper, gemstone like diamond, and many ceramic materials. In chemistry, the study of crystalline solids is important because their structure strongly influences their physical and chemical properties, which are widely applied in industries such as electronics, construction, and material science.
Now, we will be looking at the fascinating world of crystalline solids, the materials that form the bones of our technology, from silicon chips to diamond drills. First, their defining feature is a regular and orderly arrangement. Now imagine a perfectly stacked army of atoms, repeating its pattern in every direction to form a 3D grid called a crystal lattice. So this isn't just for show. This extreme order dictates everything else about the crystal. So because of this perfect internal architecture, crystals grow with definite geometric shapes, with flat faces like the hexagonal prisms of quartz or the perfect cubes of pyrite. So this external symmetry is a direct mirror of the internal atomic order. This order also means they have a sharp melting point. So unlike a glass or plastic, which often soften over a range, a crystalline solid stays rigid until at one specific temperature, the entire lattice structure collapses at once. It's a digital shift from solid to liquid. So finally, this grid-like structure leads to anisotropic properties. So this means if you test a crystal's strength, its electrical conductivity, or how it bends light, the result can change depending on which direction you test it in. Think of wood. It's much easier to split along the grain than across it, right? So crystals have a similar directional dependency on an atomic scale. Now, to understand that internal lattice, we use the concept of a unit cell, the smallest repeating block that builds up the entire crystal. In cubic system, which are common types, there are three primary types. The simplest is a simple cubic structure with atoms only at the corners. So each corner atom is shared by 8 surrounding cells. So this cell effectively contains only one whole atom. This is quite inefficient, and only a few metals, like polonium, crystallize this way. To pack atoms more efficiently, we get the body-centered cubic structure. Here we have the corner atoms plus one atom right in the center of the cube. This gives us 2 atoms per unit cell. Metals like iron, tungsten, and chromium use this strong, dense arrangement. The most efficient packing, however, for spheres of the same size is the face-centered cubic structure. Atoms are at the corners and at the center of each of the 6 faces. With shared atoms, this totals 4 atoms per unit cell. This is a hugely important structure. It's how copper, aluminum, silver, and gold crystallize, explaining their excellent ductility and conductivity. So from the external beauty of a crystal's shape to the internal logic of its atomic blueprint, we see how structure defines the properties of the materials that shape our world.
Assalamualaikum and hi. My name is Muhammad Zulhazik bin Ahmad Bakri. I would like to explain about type of crystalline solid and the example of each solid. There are 4 types of crystalline solid, such as metal solid, ionic solid, covalent network solid, and molecular solid. For metal solid, the structure of metallic crystal is often described as a uniform distribution of atomic nuclei within a sea of decolorized electrons. The atoms within such a metallic solid are held together by a unique force known as metallic bonding that gives rise to many useful and very bulk properties. Next is covalent network solid. The covalently bonded network is three-dimensional and contains a very large number of atoms. The atoms in this solid are held together by a network of covalent bonds. A covalent network crystal consists of atoms at a elliptic point of the crystal, which is atom being covalently bonded to its nearest neighbor atom. Next, ionic solid. Ionic solid are composed of positive and negative ion that are held together by electrostatic attraction, which can be quite strong. Many ionic crystals also have high melting point. Lastly is molecular solid. The intermolecular force may be dispersion force in the case of nonpolar crystal, or dipole-dipole forces in the case of polar crystal. The strength of the attractive forces between the unit percent in different crystals vary widely and indicate by the melting point of the next is example of crystalline solid. Generally, ionic crystal form from a combination of group 1 or group 2 metal and group 16 or 17 non-metal or non-metallic polyatomic ion. For example, an HCl crystal. Next is metallic solid such as crystal of copper, aluminium, and iron are formed by metal atom. Next is covalent network solid. Covalent network solid include crystal of diamond, silicon, and some other non-metal and some covalent compound such as silicon dioxide and silicon carbide. Lastly, molecular solid. Molecular solids such as ice, sucrose, and iodine are composed of neutral molecules. For example, is carbon dioxide.
Next, I will explain the differences between crystalline solids and amorphous solids. First, in terms of structure, crystalline solids have a periodic and regular arrangement of particles that extends over long distances. In contrast, amorphous solids have a random structure with no long-range order. Moving on to symmetry, crystalline solids can be anisotropic, meaning their physical properties may vary in different directions. On the other hand, amorphous solids are isotropic, so their properties are the same in all directions. For the melting point, crystalline solids have a sharp and well-defined melting point. However, amorphous solids do not melt at a single temperature. Instead, they soften and melt over a range of temperature. In terms of the type of bonding, crystalline solid may consist of covalent, ionic, metallic, or van der Waals bond arranged in a regular structure. Amorphous solids can also have covalent, ionic, metallic, or van der Waals bonds, but their arrangement is irregular. Finally, examples of crystalline solid include salt, sugar, and diamond. Examples of amorphous solids include plastic, glass, and gels. Next, I will discuss the applications of crystalline solids. Firstly, crystalline solids play a crucial role in semiconductor technology. Due to their well-ordered atomic structure, they are able to conduct electricity under specific conditions. As a result, they are widely used in electronic components such as transistors and diodes. Secondly, crystalline materials are intensively used in sensor technology. They are employed in sensors to detect temperature, pressure, and various physical or chemical parameters. Their consistent and predictable responses to external stimuli make them highly suitable for precise measurement. Another important application of crystalline solids is in jewelry and gemstones. Materials such as diamonds, rubies, and sapphire are highly valued for their excellent optical properties, as well as their high strength and durability. Finally, crystalline solids are used in optical devices, including lens, prism, and laser systems. Their ability to manipulate and control light effectively make them essential in many optical applications.
For the last part is conclusion. In conclusion, crystalline solids are solids that have an order and repeating cycle that is structure. This arrangement gives crystalline solid their definite shape and sharp melting point. There are different types of crystalline solids, and each type has its own unique properties that make it useful for different applications. Therefore, crystalline solids are very important in inorganic chemistry and play a major role in industry and everyday life.